Welcome to my talk about concurrency control and event-driven architectures. First about the contents. I will explain a bit what an event-driven architecture is. Then what are the events that are sent in an event-driven architecture. Then a bit about what concurrency control is in such an architecture. And then two strategies to have concurrency control. And ideally, you have them both. Then I showed two example architectures that use both of those strategies, and then with all the components that are involved. And then I will conclude what's there to learn. First, a bit about my event-driven architecture road. So in 2015, I started with the Rabobank. They had like this very traditional databases that were very at the core of the bank, and they had events like transactions that were done there, and they didn't want all those backend systems to be hit too hard. So by putting them as events on Kafka, they were decoupled, and I was there to set things up, starting to use Kafka and also making it running the Kafka brokers, and also make it easy to use within the Rabobank. Then at some other point in time, I moved to Payconic. That was a payment provider, and they needed a KYC functionality. So then we mainly used Mongo to store all the data. But then based on Mongo, we also created events, also like really meaningful event, like the user was subscribing to the platform, and then used event-driven architecture to make sure they were onboarded or not. And then 2022, I was joining Axonic. I already had played with it a bit, and they have more of a full solution with event sourcing integrated, which is a bit complicated sometimes to get into, but really delivers once you have it in production. So a bit on what an event-driven architecture is. Let's say you start with a very basic application, which is just to register orders, and people can also see the orders there in the backend. So then you basically just have one application, one UI, and they all share, but there are no events shared. That's pretty hard to connect to. So at some point, when we create orders, we make that into events, so it can be easily shared with other applications. So for example, one of those applications might be something to pick orders in a warehouse and make them ready. And also one of those events could also be that the order is marked as ready. But then of course, it would also be nice for users if they get some feedback. So having that central storage, which could be something like an event bus and all streaming, or an event store that's basically just about which kind of API you're using to get those events and to store those events. You could then add a third application that would see, oh, the order is now sent. I can send an email, it's updated. Or you could have something based on time that if after a week it's still not completed, it would say, well, we're trying to complete your order, or you give some notification somewhere to the backend with this order is still open. So then you can build on like that based on those events with small applications that are really suited for that purpose, without creating a big monolith that's hard to maintain. So some of the benefits of event-driven architecture. So you have the decoupling. So you can have different kind of applications that you can easily scale up and down, and that don't share much of the data. So you can also easily scale those applications. So probably creating the orders will happen much more often than what needs to go in the backend. So then you can scale the one for creating the orders, for example, when it's Black Friday, without needing to scale up all the kind of applications if you would have a monolith. It's also more resilient. So if one of those applications goes down, another can easily pick this up, since the events are what's shared. So instead of they don't each application doesn't need to process all the events, so they each get their share. So if you have 2 applications, they each get half. If you have 3 applications, they each get a third. So it's easy if one falls away, then the other still can go on, and you won't lose anything. And one of the other benefits can be that the history is available. So that's especially convenient for auditing, like with banking or other stuff. But also if you want to change your projection or other things, it's sometimes very easy to know the changes, but also why it's just changed. Some of the challenges of event-driven architectures are who maintains the middleware. So it doesn't really maintain what that central piece is, and if it's more like a bus or more like a store, but it's something that's used by multiple teams. There is someone that needs to set some rules about the format used, about authorization and things, even if you use cloud provider. So yeah, it needs to be clear, and there needs to be some process managed to get there. Instead of if you would have just only REST endpoints for every application and anybody just doing their own thing. And also how to test individual servers could be a challenge, since, well, they are based on events, and that event might come from other servers. So if you want to test them, you probably need to know which kind of events would have happened, put them in something, and then test what the servers that you're working on needs to do. And then also test the outcoming events or whatever your application is doing to be sure that it's working correctly, which is harder than when it's all integrated in one big application, or it can be hard. So then what are events? And for this example, I used the cloud event, but basically whatever kind of event you have, you need to have something like that. So with cloud events, you have a spec version. So then if something changes on the specification, you know that it has been changed. And when you can see that the spec version is 1.0, you can make certain assumptions on what else is there in the message. Then there should always be a type. This could be implicit, but most of the times it's explicit in the event, so that you know what kind of thing is this. And here it's a stickered ordered event, because the example I will use will be some application that's used to order stickers. We'll get more on that later. Then a source, because if it's distributed, you don't really know where that event is coming from, and you want to know which schema it has or something. Then it's easy if you can point to a source, which could be something like a GitHub repo, but it could also be something else, as long as you know there's some kind of way to get to the definition of that event. Then an ID, especially to deduplicate messages. It's always nice if they have a unique ID, because then just by that property, you can know if 2 events are really the same event, or are really different events that just happen to have the other properties in common. Then a time. Of course, events is always something that has happened in the past. So then it's nice to have a timestamp. Also, if, for example, something screws up the ordering, then you still can fall back on the time, so you know that this event really happened before this event. Then some connected ones, data content type and the data. This could, of course, also be already as part of a specification implicitly, or as part of the type. But it could also be concrete, that you say, really, this the data that's contained in this event is in JSON, and then with the data also. But it could also be a binary or something else. And instead of data, it could also be a payload field or something else. But yeah, the data needs to also be there in some way. How are events created? There are several ways. So it could be a mapped external event. So something is happening outside of the domain of the application. And for example, by a REST call or something, that event is created. It could be an internal event. So really something that's created from the application itself. It could be based on the time and state of the application. For example, if you have the ordering system and after a week you don't have anything, then the trigger is kind of the passing of that week without anything happening. That could also create an event. And the one will be mostly talking about is the result of a command like invocation. So that's basically saying, I want to create an order, and then the order might be created. But it might also be that I don't have the rights to create an order or something else, and then the event won't be created. So now a bit about concurrency control in such an architecture. So there's the boundary, there's two kind of applications, because that's important, because you don't want to have them both interfere. There's a central component, which could be event store or event bus. And then there's a third application reading all the events. Now, if there is no concurrency control, it could be that you have a similar like command fired to both applications, and that they both create an event message that's written to the event bus. And then the third application gets into error states. For example, if you have, in the example we will be using, which is about stickers, and then you start with 50 credits, and you can never have below 0 credits. And then if you order stickers, they cost 30 credits. So then you would have both times 30 credits, so you would be -10, but that's kind of impossible. But since they're both handled at the same time, both using the same store, and there's nothing in between, it's possible for those messages to be created. And then you get in an error state. And of course, that's not something you want. So what can you do about it? So again, this is the sticker problem. So in this case, there's a memory created. By default, this has 50 credits. Then one of those order stickers command is issued, and then it's fine. The 30 credits are subtracted, and then a sticker ordered event is created, and that's all fine. But then a second time, when that command is struck, then there are insufficient credits. So it should return some kind of error, but at least not create a second of such an event. So one way to do this is by either on the bus or the store, create optimistic locking, so that if on the same application those would be invoked, then there would be a central component which is an aggregate for people that know what an aggregate is, and that has a version number. So in every kind of sticker command for the same person would end up with the same record, basically. And there's also a version kept in there. So one of those applications is earlier and will write with the new version. And if the other one tries to update, but the version is not correct, it will fail. And then it has to reread, and it can check if it's still valid with the new added event. And then if it's still valid, it can update. But if it's not, it fails and the event will never be appended. So this is a very nice way to use optimistic locking on the database to prevent those concurrent writes. A second approach is to make sure that all those commands are handled by the same application. So then that application will just, since the state within that application will stay correct, then every time the first one will succeed and the second time won't succeed. So that second command will block also, because if it's all async, then it also won't work. So it has to block for the one to succeed, then try the second one, and then see that it doesn't succeed. But both have their disadvantages. So you probably want to use them both. Because with optimistic locking, it's possible that you keep retrying. So it could be that you have 10 or maybe even more than 10 changes for the same aggregate at the same time. And then they each have to retry again. If you have a lot of applications and there are a lot of instances trying to hit the same one. And the big disadvantage of the single writer principle, because then everything would end up with the same instance. So it would the writes would succeed each time. But then if you don't have the optimistic locking in place, if by some scaling problem or rate thing, you still have two applications getting hit with the same command, it would still succeed. So it would be nice just as fallback to be truly sure that it's always behaving properly, to also have those optimistic locking in place. So using them both. So one of the ways to use them both is to use a relational database where you can use transactions for the optimistic concurrency, and then use Kafka to really make them turn those into events via the Bayesian. So the Bayesian will look into the change log of your database, and then you can grab those things and basically change them into events, making sure that it's consistent with the database. And then Kafka can be used to share those events with other applications. So in this case, we have a command like invocation, so that can be something like a REST call to application. Then Postgres that will write a message. So there we deal with optimistic concurrency. And then we can use Kafka Connect that will pick up the changes from Postgres. So Kafka Connect is a way to use the Bayesian to easily start it up. And then from the Kafka Connect, we can write it, that will write change as a big JSON, but that has too much data in it for other applications to use. So basically we use, and then Kafka streams to turn the whole change into just the bits that we need, and maybe also use schema to make it easy to also evolve the schema and make it easily readable for later. And then, yeah. So this is the stick ordered event, making it transactional. So then we get an identity manager and use optimistic locking there. And then if the registration is null, then there's no registration. So then there's no event. If the credits is less than the sticker price, then it's also not sufficient. But then if it's fine, then we create, we both change the credits that are deducted by 30, and we also make it create a stickers ordered event. And that stickers ordered event, since it's created in the same transaction, we can then use it via the Bayesian to share it with other applications, and then we're sure they're always in sync. The second example architecture will use Axon Framework and Axon Server. So I will first, since there was less common, share a bit of information about both. The Axon Framework is actually more than a decade old. It's a Java framework, and especially if you use it with Spring Boot, it's very easy to use and configure. And it's combining things, ideas about domain-driven design, CQRS, and event sourcing. And for this part, it's important that you have this entity. It's called an aggregate. So there you're building up states based on events. And then you use a command bus, and that's basically sending a message to such an application that has an aggregate to check if the command is valid or not, and then create events or not. And then one way to use the Axon framework, because you can also use it with, for example, a Postgres database, and then use Kafka as a message bus, but you can also use Axon Server as the event source and also to route the events, and then you get that. And this has also some other advantages, like you can easily see which applications are connected, and you can also make it, you can use a cluster and then have it highly available. So with Axon Server, you would still have the same command-like invocation, but then that would trigger a command that's sent via the command bus via Axon Server. And that will use a routing mechanism that makes sure that if it's for the same aggregate, it goes to the same handling application. But of course, if you're just scaling up or scaling down, it could miss something there. And then it would update, create the event, and return that the command is handled properly. And then other applications can that are subscribed can get the stickers ordered event. So with Axon, this is the command handler. So this is part of the aggregate that will handle the command, and that will first try to get all the events, build up a certain state, and then it can check if the credits are lower than the sticker price, then it's insufficient, and otherwise it can apply that new event. And then it will actually, if it happens that you're just scaling up or down, and both two applications still get the same command for the same aggregate, then only one of those applies will succeed and the other one will fail. Since underneath there will be checked, there will be optimistic concurrency in place, where you get basically for free, because that's already configured for you. And then one of those will fail and the other one will succeed. And this is the event sourcing handler. So that's how you can build up the state. So that's also here where you have the stickers order events that will reduce those credits. So a bit on the command routing. So from the Axon framework, we can determine a routing strategy. And most of the time that will be using the aggregate ID to route the message. That will be sent along with the priority to Axon Server, and that will make sure it handles with one of those instances. And if it's then a second call belonging to another aggregate, it could handle land on another application. But if it's for the same aggregate, it will always go to the same application, as long as the same amount of applications are running. So then you get the best of both. So that's nice. What's there to learn? How do the example architectures compare? As you could see with the Kafka one, you have quite some things to set up and think about, especially to make the BCM event something that's usable for other applications. So that's something to take in mind. And with Axon, it's a bit easier. You do with Axon kind of tie into the GVM, but it's possible to use Jackson as serializer. So then all your events are JSON, and then it's with Synapse or with using the Kafka extension. Then it's easy to also share it with other teams in a good, nice way. There is a demo application. So currently that's only containing the Axon variant. If I have a lot of time, then I might also add the Kafka variant there. There's also a white paper, so explicitly about the concurrency control with, at some levels, some more insights. What else is there? I know Akka also has some things to at least get the event routing correctly set and easily set up. Of course, you can also build your own solution, but since it's quite complicated and it's also something that really needs to go correct all the time, it's very hard to prove that it's really working in a distributed system. So that's probably won't be wise. I don't have any experience setting up this self with Akka, so I'm also not sure how it compares to the other ones. Then the big question, do you really need all this? That of course depends on your domain and how easy it is to, in the case of errors, how easy it is to fix those errors. But
probably if you use something with those command-like invocations, it's very nice. Of course, you don't necessarily need those command-like invocations to create events. If it's just a simple REST application, you might get away with it. But yeah, if you want to be event-driven all the way, you probably need so. For questions, you could email me or reach me out on Twitter. And we also have a Discuss platform specific for Axon Framework, Axon Server, where we also happily take questions.